Hey, how's it going? What's up? It's me. Welcome back, Wolfpack, for another stream. It's me. My name is Key, and I'm here to do a little study stream today. Also, I'm practicing on my new Moonlander keyboard. It's an Ergo keyboard, this thing right here. It's super cool. I just got it, and it's very different from a normal keyboard because the layout is both ortholinear. Think that's what it's called. No, it's a grid. It's not technically ortholinear. It's a grid, and it's split. And the thumb clusters have a lot of keys that you're probably used to using your pinky to type on. So it basically, I'm going to be doing a study session, and while I do this study session, it's kind of going to be an excuse to practice my typing, which is something I'm going to be trying to work on basically until I get back to my regular typing speed and accuracy. So it's like the best of both worlds, two for one special. If you look down here, this will actually show the keys as I press them. Um, it's probably a little hard to see. Let me actually reconnect. It seemed like this wasn't. Okay, there it is. So now it'll show the keys as I press them, and you can kind of see what my hands are doing. So this is the Moonlander keyboard, and this is their software that they have for it as well. In this software, as well as their online application, you can actually download different keyboard layouts. So if you want to do a standard layout, if you want to do a Colmac layout, a Dvorak layout, Workman, any of those, you could just literally go to their website and download one, like a layout that someone else has made, and like you can instantly start using it. And you can buy blank keys as well. I'm just going to stick with what's, standard out of the box. Maybe I'll change to one of those things later on. But for now, I don't want to make that big of a leap because I'm already disrupting my process by changing my keyboard in general and using them. So I just have to kind of come to grips with what I currently am doing before I try to make this any more complicated. So, but anyways, I'm going to take my notes here and study. So it's the boring stream. You already know what it is. It's operating system concepts and the Moonlander keyboard. Okay. Hopefully you brought a snack. And yeah, hit me up in the chat. Let's talk. Okay. So I already started studying this book a little bit before. I didn't make much headway, but I know what the book is kind of about as a whole. That's not the zoom I want. I want maybe I just need it a little taller. There we go. Okay, so operating systems are an essential part of any computer system. Yeah, I'm gonna skip this whole intro section. I just want to go to chapter 1, basically. I thought I had like an outline. There it is. Okay. That was weird. That is not a good UI. Look at this. How am I supposed to know that this is a drop down? You can barely see that. Okay, so we want to do single page. I do not want to scroll, that's for sure. Okay, so contents, part 1. Whoever put this PDF together, they did their thing. They did their big one with this. They definitely got all the sections outlined here. This is what I like to see with a PDF. If you're a real student, this is good. This is perfect. This is exactly how it should look. This is perfect. It's skimmable. That's my $5,000 word for the day, skimmable. Did I forget to? Oh, okay. I thought I forgot to enable the chat. Let me put a question in here. before I start this. What y'all studying? I want to know. What are you studying these days? Let me know in the chat, whether in the present or in the future. Just go ahead and leave a comment. I want to see. Okay, so when beginning our discussion by looking at the operating system, we begin our discussion by looking at the operating system's role in the overall computer system. A computer system can be divided roughly into 4 components. Okay, I gotta type this. I've been doing a lot of typing games, so hopefully they helped. Ooh. Four main components. Enter. Oops, nope, that wasn't it. That must have been. What was that I hit? What did I just? Oh, I hit the tab. Okay, how do I do Command Z? Oh, there you go. Okay, enter. I need a dash, space. Okay, so hardware. So if I wanted to really understand computers, I would need to study all of these areas, basically. Basically, is what I'm hearing. Application programs. And, oh, the user. Interesting, okay. User. The hardware, the central processing unit, the memory, and the input-output devices. Okay, how we go up? See, now, next time I do my notes, I'm going to try to do it in Vim, because then I'll get that practice too. Tab, where's my tab? Okay. So for the hardware, the CPU, memory, input, parentheses, IO. Okay. Excuse me. So those are the basic compute resources for a computer. Application programs. Okay. What? Too far. So we need to go down, over. Man, kind of feeling like I should be doing this in Vim because this is already hard. I'm already looking at my hand, so what difference would it make? Okay. Word processors, spreadsheet compilers, the ways in which these resources are used to solve users' computer problems. Okay. The ways. Hardware. I feel like my my apostrophe button sometimes doesn't want to doesn't want to do anything. I'm not quite sure why. I think it probably has something to do with whether or not I'm holding it or tapping it or something. But I feel like it gets sticky sometimes. So the users, computing problems. Okay. Oh, that's interesting. Okay. So the operating system controls the hardware and coordinates use among the various applications. Back up. Uses. Oh gosh, this keyboard is so awkward. Or I'm the one that's awkward. Okay, uses. Various applications for various users. Okay. I think my keyboard also has a, so there's different layers. This is layer 1. This is like my symbol number layer. And then there's another one. No, that's the same one. Where is it? No, that's not it. Here it is. This is like the layer that has my, I can use my keyboard to control my mouse, which is pretty cool. Okay, now I gotta undo all that stuff I just did. Yeah, that's pretty dope. I don't know if I'll actually use this, but you can also do right and left clicks too. Uh-oh. That's cool. Okay. So the operating system controls and coordinates the hardware that is being used by the various applications. And then the application programs use the hardware resources to solve users' computing problems, and the hardware is CPU, memory, input, output. We can also view a computer system as consisting of hardware, software, and data. Hardware, software, and data. And data. Is there a shortcut for this? Is there a shortcut for the highlightion? I don't think there is. Well, that is a missed opportunity. Anyways, okay, little beach ball of death for a second. Hold on. Okay, an operating system is similar to a government. Like a government, it performs no useful function by itself. It simply provides an environment within which other programs can do useful work. To understand more fully the operating system's role, we next explore operating systems from two viewpoints: that of the user and that of the system. The user's view. The user's view of the computer varies according to the interface being used. Okay. Such a system is designed for one user to monopolize its resources. The goal is to maximize the work or play that the user is performing. Ease of use. How long are these sections? Do I want to do a note for each section? I think I will. I'm gonna do like a section for all of 1-1, I guess. Yeah. Where's my hash symbol? Okay, so let's say the users. This is tougher than it looks. So users view, where's my colon? There you go. Users view. Sure. Tab. I have a tendency to really lean forward, which is not great for my posture. Probably need to make this text a little larger for my old man eyes. With some attention paid to performance and security and none paid to resource utilization. Okay, how do I do Command Shift 4? Nope, that wasn't it. Command C. There you go. So Command Shift 4. There you go. Okay. So application programs. Sure, operating system, computer hardware. Abstract view of the components of a computer system. This is going to be a very slow read this way. I might need to just read ahead, come back and I need to read, highlight, and then type out a summary of what I highlighted. I think that's going to be my approach because otherwise it's going to be very slow. It's going to be very, very slow. Increasingly, many users interact with mobile devices. That's funny. I think that is kind of the thing people do mostly now. This book was written like a while back. Devices that are replacing desktops and laptop computer systems for some users. These devices are typically connected to networks through cellular or wireless technologies. The user interface for mobile computers generally features a touchscreen where the user interacts with the system by pressing and swiping fingers across the screen rather than using a physical keyboard and mouse. Many mobile devices also allow users to interact through a voice recognition interface, such as Apple's Siri. Make sure mine didn't go off. Some computers have little or no user view. For example, embedded computers and home devices and automobiles may have numeric keypads and may turn indicator lights on or off to show status, but they and their operating systems and applications are designed primarily to run without user intervention. Embedded computers. That's an interesting point. I kind of messed up my list by adding that picture in the middle of it, but it's fine. Did I spell embedded? I did spell it wrong. I forgot a D. I am learning that I am like a terrible typer when I'm being observed, because I'm also a really bad typer when I'm like teaching sometimes. Okay. Embedded computers and home devices are designed to From the computer's point of view, the operating system is a program most intimately involved with the hardware. In this context, we can view an operating system as a resource allocator. Resource allocator. Ah! This is only day 3 of me using this keyboard, by the way, so don't judge me too harshly. Okay. system is a control program. Okay. I never thought of it like that, but that makes perfect sense. So it's a control program and it's also a resource allocator. It's both of them. Okay. By now, you can probably see that the term operating system covers many roles and functions. In this case, at least in part, because of the myriad designs and uses of computers. Computers are present within toasters, cars, ships, spacecraft, homes, and businesses. They are the basis for the game machines, cable, TV tuners, and industrial control systems. To explain this diversity, we can turn to the history of computers. Although computers have a relatively short history, they have evolved rapidly. Computing started as an experiment to determine what could be done and quickly moved to fixed purpose systems for military use, such as code breaking and trajectory plotting, and government uses such as census calculation. Those early computers evolved into general purpose multifunction mainframes, and that's when operating systems were born. In the 1960s, Moore's law predicted that the number of transistors on an integrated circuit would double every 18 months, and that prediction has held true. Computers gained in functionality and shrank in size, leading to a vast number of uses and a vast number and variety of operating systems. See Appendix A for more details on the history of operating systems. How then can we define what an operating system is? In general, we have no completely adequate definition of an operating system. How do I do Command C? Maybe I should just do that. Command C and Command B. Oh, that didn't come out very good. Command Z. We gotta type it out. No, let's just highlight it and I'll come back. Okay. Yeah, we'll do that. We'll highlight the whole section up to 1.2 and then we'll come back and type whatever we gotta type. Because they offer a reasonable way to solve problems of creating a usable computer system. The fundamental goal of computer systems is to execute programs and to make solving user problems easier. Computer hardware is constructed towards this goal. Since bare hardware alone is not particularly easy to use, application programs are developed. These programs require certain common operations, such as those of controlling the I/O devices. The common functions of controlling and allocating resources are then brought together into one piece of software, the operating system. In addition, we have no universally accepted definition of what is part of the operating system. A simple viewpoint is that it includes everything a vendor ships when you order the operating system. The features included, however, vary greatly across systems. Some systems take up less than a megabyte of space and lack a full screen editor, whereas others require gigabytes of space and are based entirely on graphical windowing systems. The more common definition, and the one that we usually follow, is that the operating system is the one program running at all times on the computer. I like that. It is the one program running at all times on the computer. Usually call it the kernel. Okay, so along with the kernel, I feel like that's the thing. When I hear the kernel, I still feel like that's not a good definition. Let's go to Cloud and see what Cloud has to say. Cloud.ai. Can you tell me more specifically, I spelled that wrong, what the kernel of an OS is? Let's see what Claude has to say. Okay. The kernel is the core component of the operating system. It's essentially the heart of the operating system that controls everything else. Here are the key things a kernel does: memory management, process management, device management, and system calls. Okay. Okay. It's the main thing. It's the main. Okay. The kernel. The matter of what contributes in the matter of what constitutes an operating system became increasingly important as personal computers became more widespread and operating systems grew increasingly sophisticated. In 1998, the United States Department of Justice filed suit against Microsoft, in essence claiming that Microsoft included too much functionality in its operating system and thus prevented application vendors from competing. For example, a web browser was an integral part of Microsoft's operating system. As a result, Microsoft was found guilty of using its operating system monopoly to limit competition. That's very interesting. Ooh, that would be an interesting case to look into. I definitely would want to know more about that. I feel like I remember that, but I was like also like 8 or 9 when that happened. But I do remember that being like a thing. I didn't know it was about this specific thing though. I thought it was about something else. I thought it was just about like the company being too big as a monopoly in general. Let's go ahead and put a highlight on that too, because it's an interesting little morsel. It's delicious. Love a good fact. Okay, so today, however, if we look at operating systems for mobile devices, we see that once again the number of features constituting the operating system is increasing. Mobile operating systems often include not only a core kernel, but also middleware, a set of software frameworks that provide additional service to application developers. For example, each of the 2 most prominent mobile systems, Apple's iOS and Google's Android, features a core kernel along with middleware that supports databases, multimedia, and graphics. In summary, for our purposes, the operating system includes the always running kernel, middleware frameworks that ease application development and provide features, and system programs that aid in managing the system while it's running. Most of this text is concerned with the kernel of general purpose operating systems, but other components are discussed and needed to fully explain operating system design and operation. I hate when textbooks do this, where they're like, hey, here's a little fun fact in an extra special place block or whatever, but it's like right in the middle of a paragraph, so I have to remember to come back to it. Or if I try to read it in the moment, I'm at the risk of going on a tangent, because sometimes there are especially juicy facts and figures in them. First world problems. Okay. Why why study operating systems? Although there are many practitioners of computer science, only a small percentage of them will be involved in the creation of or modification of an operating system. Why then operating systems? Why then study operating systems and how they work? Simply because, as almost all code runs on top of an operating system, knowledge of how operating systems work is crucial to proper, efficient, effective, and secure programming. Understanding the fundamentals of operating systems, how they drive computer hardware, and what they provide to applications is not only essential to those who program them, but also highly useful to those who write programs on them and use them. Okay. Okay, so let's see what we got here. Let's see what things we got. Um, let's just. Oops. Nope, that wasn't it. How do I do. Nope. I need to do back tab. Can I do this? Nope, that didn't work. Nope, that didn't work. Back tab. That didn't work either. I thought it was Shift Tab. I did it on my other keyboard, it worked. Shift. Oh, maybe I didn't. Maybe I didn't do it the right way. There it goes. Okay. Shift Tab. So let's say there is no complete there's no complete adequate definition of an operating system. That's kind of wild to think about. I never really would have thought of that. There's no completely adequate definition of an operating system. Okay, so I've been streaming for 40 minutes. That's wild. Okay, let's resources. Okay, it's the one program that runs all other programs. Running at all times. Microsoft includes too much functionality. Okay, middleware. Oh, where are my stars? There you go. Okay. I think we're good on that. So we're got a new section here. Hash symbol. 1 point. Computer system organization. One or more CPUs and a number of device controllers connected through a common bus. That provides access between components and shared memory. Each device controller is in charge of a specific type of device. For example, a hard disk. You know what? I need to use Speechify. I have it for a reason. Wait. Hold on. Okay, that's not what I want. Give me 1 second. Because I'm not about to play these games with this thing over here. Let's go ahead and... I don't know if I can actually save my notes and have them show up in Chrome. But we about to see. I'm on page 7 because, you know, Speechify is for people like me who have dyslexia in the family. I don't know if I have dyslexia, but I got enough of it. Feels close enough, like it sometimes. My dad has dyslexia. Oh, look at that. It preserved my highlightations. Glory be. Glory be. But it won't let me do highlightations in here. That's unfortunate. That's very unfortunate. That's very unfortunate. But, you know, it is what it is. So let's get Speechify going on here. Why don't I see Speechify? Okay. Why don't you show up? Oh, child, I don't know. Normally it just shows up in the corner. Yeah, normally it shows up in, oh, there it is. Okay, so now it shows up, but it don't show up on this page. Does it not read PDFs? Oh, no. Oh, Lord. Okay, I'm gonna have to do this off screen. Give me just a moment here. Actually, I'm gonna take a break. It's about that time anyways. When I come back, I'll have Speechify because we about to really get it cracking and popping. Snap cracking and popping. Okay, so don't go too far. If you do, you know, you always gotta come back to the wolf pack. Oh.
A modern general-purpose
computer system consists of one or more CPUs and a number of devices.
Yo, 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 yo. I'm back. I'm back. And I got Speechify working, which is great. Um, so, with that being said, I can resume my studies. And now it'll be a little bit more efficient. Okay, so let's go ahead and start here. Let's do this whole thing right here, basically.
A modern general-purpose computer system consists of one or more CPUs and a number of device controllers connected through a common bus that provides access between components and shared memory, figure 1.2. Each device controller is in charge of a species type of device. For example, a
That's
display,
not the right word.
audio device, or graphics display. Depending on the controller, more than one device may be
This
attached.
is Obama's
For instance,
voice.
one system USB port can connect to a USB hub to which several devices can connect. A device controller maintains some local buffer storage and a set of special purpose registers. The device controller is responsible for moving the data between the peripheral devices that it controls and its local buffer storage. Typically, operating systems have a device driver for each device controller. This device driver understands the device controller and provides the rest of the operating system with a uniform interface to the device.
Do, 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 banana. Someone told me the other day that they sing whenever they're studying or coding, and I was like, "That's the vibe." I kind of do that too. I don't do it on the stream a lot because I'm very shy about singing, but yeah, I totally get it. I'm very active when I code. I don't just sit there. I like move around and sing and stuff. Okay, so the CPU device controllers can execute in parallel. Okay. The memory controller synchronizes access to memory. Okay. I'm going to have to unpack that part. Um, not quite sure about that. Like, I know what those words mean, but I just need a more specific example. Let's make that underlined. Did it underline? It didn't underline, did it? Let me try it again. There you go. Okay. In the following subsections, we describe some basics of how such a system operates, focusing on three aspects of the system. We start with interrupts, which alert the CPU to events that require attention. We then discuss storage structure and I/O structure. Is there a shortcut to underline in Apple Preview? Let's look that up. It's weird that I enjoy having an obscure keyboard, but like basically there could be no lower level of disinterest that a person could have than I have for actually wanting to set up customized shortcuts for any app ever whatsoever. I do not like it. It makes me feel stressed out. There's too many things that already have preset shortcuts for keys, and I just don't even want to get in the hassle of trying to manage and sort all of that. So I just avoid it at all costs. But sometimes being able to do that, being willing to do that is what's needed. Let's see. Is there a thing in here where I can even set the shortcut? I don't think there is. Okay. Well. Oh wait. So there's no way I could set a shortcut. Can we look in here in the key? Nope. First of all, there's an app for this inside of the computer already for Apple. When did they get documentation for things in the actual operate? Okay, that's new to me. Um, Maybe I need like a PDF reader. Ugh. I feel like if I get a PDF reader, it's just gonna have like ads in it or some shit. Let's just check it out. Well, let's just Google it. PDF viewer. Maybe I could just do something in VS Code, maybe. Why do I feel weary of downloading Acrobat Reader? I'm gonna do it anyways, but I don't want to. Is it like the best one still? Yeah, I don't need like all the features in the world. Well, maybe it's just gonna have to be an Acrobat Reader. Dang, that was half a gig. That's wild. Okay, let's get this installed and stizzled. Let's get the Acrobizzle, Redizzle, and Stizzled on my computer rizzle. For shizzle. I still have my regular keyboard down here in the corner as well, because there's just some things that I just need to have it to do for me off screen, like passwords and stuff. Dang, this is taking a while to install. It says less than a minute left. Boop. Boop-a-doop. Boop-a-doop, bing bong. Okay, it's almost done. Come on. Come on. Chum on. Chum on. I wish there was like a way where you could use an application that is streamed to your system as you use it, so that it does not need to be fully downloaded for you to start to use it. And then as you use the application, it'll like try to predict what parts of the app you're going to use, and it'll install those pieces as you use them. Like a lazy installation type of thing. That would be so nice to have. That would be so nice. Somebody needs to invent that. Because then you wouldn't have to, like if you're using any app, there could be like possibly a way to use it before it's fully installed in your system. And maybe there's like a gated experience that expands as the software installs, especially for like really big things. That'd be so nice. Like a soft install, like a streaming install, something like that. Okay, anyways, we have it installed now, so let's go and get that thing. Let's get that thing. Let's get it. Let's get it. Kitty. I wonder if it'll take my Apple highlightations now. Is highlightations a word? Okay, let's agree. Yep. Ooh, look at this. This is giving me very much business professional. I don't want it to be my default. None of that over here. No, thank you. And how do I open? Let me bring this over here. How do I open stuff? Oh, let me do it on off screen. I don't want y'all in my business. I gotta sign in. Oh, I don't have to sign in. Okay, good. About to say, I ain't signing up for shit. Not right now. I'm tired of signing up for things. I'm gonna be honest. I don't know why, but I feel like a sense of fatigue when it comes to giving out my, especially all the dang spam. I get so much spam and email for things that it's like, I want to use your very specific product. I don't actually care about your whole business spiel. I just want this very specific piece of software, product, solution, whatever have you. I don't want everything. I don't want monthly updates for a piece of software that I also wish I didn't even have to get in the first place. Why do I need a chatbot or an AI bot? I just want to read the PDF. Okay, you try to give me everything but what I asked for. That's how I honestly feel. So, yeah, I don't want to sign up for nothing. I do not. No, thank you. Y'all want my phone number, social security card, address, my daddy address. Y'all want my social security number, passport, driver's license ID, employee staff number, salary. You know, damn. Just to use any kind of app. Yeah, that's one of the things that irks me these days. It's having to surrender a bunch of information. And then I was like, what is it being used for? Why do you need all of my business just for me to read a PDF? Come on now. Come on, child. Okay, so this is a nicer experience. I just really wanted the shortcut for the highlighter. Can I at least get that? I just need to know where the key map is. You know, the funny thing about software is that we definitely have existed in a maximalist era for software for a very long time, where it's just like a lot of software is so bloated. I feel like if you come up with a good solution, your software should not feel bloated. It should feel very light. Very light, and there should be diverse options as well from many different vendors. It shouldn't be like just one big monolithic mega app for everything. That's just, it's kind of gross. Where are my shortcuts? That didn't do nothing. Okay, well. Acrobat Reader highlight shortcut. Booby dooby doo. Booby dooby doo. Dooby 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 doo. Dooby doo. Dooby doo. I promise one day I'm gonna do a whole album that's gonna be like lo-fi beats, but with me singing on it. Okay, so it says here, go to edit preferences. Okay, so preferences, under the general tab, select the use single key accelerators to access tools, and then shift U for highlighting. Okay, cash me outside, how about that? Oh, it kept my highlightations. Hey, that's what I'm talking about. Y'all did at least one good thing for me. Out of all the decades that you've been around, y'all did this one good thing. Y'all could at least say that. I give you your credit, Adobe. You kept my highlightations. There must be some type of universal PDF highlightation format, framework of sorts. That's a beautiful thing. Okay, so let's try it. Control U. Did that work? Oh, it worked. Okay, so Command Z, and then Control Oh, okay. Where's my preview? Okay, that's not what I want. View. Sidebar. I don't want no scrolling. Don't give me none of that. Nope, that was not what I wanted. Okay, I want that, and I also want the sidebar. I feel like such a elderly person right now. Okay, side menu bar, side panels. Model tree. Is that what I want? That's not what I want. Model. See, y'all doing way too much. Y'all are doing way too much. What is this? Okay, that's not what I want. What is this? That getting close. There we go. Why is this on that side? I feel like this is something that belongs on the left side. I'm stressed out. Okay, so where was we? Right here, right here, right here. Okay, I just gotta get that command down a little bit more smoothly. Oh, wait, if you just drag, that automatically highlights. Oh, okay, that's not too bad. I like that. I don't like the color. Let's do that. Okay. Okay, so we got something going on here. Okay, cool. Okay, let's get back to this. Now I'm hungry. Okay, consider a typical computer operation, a program performing I/O. To start an I/O operation, let's take this here and let's do this. So if I do this, I could just do it like that. Oh, I'll just talk about awesome. This is much better. I should have been here a long time ago. Okay, now I think we can do this with Speechify.
The device controller maintains some local buffer storage and a set of special purpose registers.
Nope.
The device controller is responsible for moving the data between the peripheral devices that it controls.
See, they should just go ahead and put the AI voice thing inside of Acrobat.
Computer operation, a program
That'd be better.
performing I/O. To start an I/O operation, the device driver loads the appropriate registers in the device controller. The device controller, in turn, examines the contents of these registers to determine what action to take, such as read a character from the keyboard. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver that it has finished its operation. The device driver then gives control to other parts of the operating system, possibly returning the data or a pointer to the data if the operation was a read. For other operations, the device driver returns status information such as write completed successfully or device busy. But how does the controller inform the device driver that it has finished its operation? This is accomplished via interrupt. 1.2.1.1 overview hardware.
Okay. So to start an I/O operation, device driver loads the appropriate registers in the device controller. Okay, the device driver is the part that is installed on the system that basically provides a universal interface for the device. And the device driver loads the appropriate registers in the device controller. So the controller is what is in the actual device. Okay, the device controller in turn examines the contents of these registers to determine what action to take. I guess that's a question. Is the device controller in the operating system or is it in the device? Okay. The device driver then gives control to other parts of the operating system, possibly returning the data or the pointer to the data if the operation was a read. Yeah, that makes sense. But how does the controller inform the device driver that it has finished its operation? This is accomplished via an interrupt. Okay. Oh, I can leave comments too. Hey, that's well. That that might be kind of a nice way to study this. No, it's got me thinking now. Maybe I could just do my notes in the comments. That's it. Maybe I'll try that later on. I'm not gonna do it now, but that is interesting to think about. Okay, so let's go ahead and do this next section here. This next secciones. I guess I can't get it all. Let's just try to go. Will it let me? Won't let me go up. Okay. That's fine. We'll just take it like this. I don't want to rate your software. Oh gosh, you're ruining my
signal to the CPU, usually by way of the system bus. There may be many buses within a computer system, but the system bus is the main communications path between the major components. Interrupts are used for many other purposes as well, and are a key part of how operating systems and hardware interact. When the CPU is interrupted, it stops what it is doing and immediately transfers execution to AZD location. The exceed location usually contains the 1.2.1.1 overview. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. There may be many buses within a computer system, but the system bus is the main communications path between the major components. Interrupts are used for many other purposes as well, and are a key part of how operating systems and hardware interact. When the CPU is interrupted, it stops what it is doing and immediately transfers execution to AD location.
This is really struggling to read.
DD location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes the interrupted computation. A timeline of this operation is shown in Figure 1.3. To run the animation associated with this GUR, please click here.
Okay, I'm gonna try something else because this is definitely not giving me what I need to get. It's not giving me what I need to get from it. So I'm gonna take this and I'm gonna try to do this another way. Okay, so instead of doing Obsidian, because clearly we don't need him at the moment, I'm just gonna close that. This can be kind of over here. We don't really need this too much. And what I'm gonna do is I'm gonna bring in the Speechify app, and I'm just gonna upload my PDF to it, and just do the reading directly out of it. Because I think what's happening is it's having to buffer because it's only able to send a certain amount of context, and then it's causing it to break up the reading in like really weird ways. So that's, I will not stand for it. I will not stand for it. So give me 1 second. I'm sure somebody at Speechify is like, dang, this guy is uploading, downloading all kind of books. By the way, I got this book from the Creative Commons. Okay, I got this from archive.org. I mean, I googled it, but it was on there, and I saw that this book was everywhere for free. So I just took it at face value, but that's how I got it. I ain't gonna lie. I don't know if I'm allowed to put it on Speechify, but that's why I got Speechify. So hopefully they let me keep it. So then what I could do is I could have it over here. I don't think I could do. I don't think you can do highlightations in this,
The
but that
hardware
is just
knowledge required.
fine. That's fine by me. What I do need to do is find the page though. And then I could try to do the notes over here, I guess. We'll see how that works. Let's try it this way. I am such a nerd about this. Oh, it kept my highlightations in here as well. That's kind of interesting. Maybe I need to email somebody at Speechify and say, hey, can you add highlightations, highlight? Oh, there is one. Text highlight. Oh, but I can't do it. Oh man, if I could do text highlighting in here, that'd be a game changer. It must be in here somewhere. Don't play with it. Please don't play with it. Y'all teasing me. It's not. Oh man, that sucks. That's a bummer. I need to see if Speechify is hiring. Maybe I need to be the one that goes over there and does that for them. Okay, it's cool, I guess. Okay, so let's go ahead and have it start. Oh, what was that?
Consider a typical computer operation, a program performing I/O.
Oh, I put my voice in here too, so we can make it sound like me. I didn't use like my real voice. I made myself talk like in a stranger way than I normally talk, so because I didn't want my exact voice in there. But yep, it's in here.
Hi, my name is Ophelius. I am an English voice from the United States.
That sounds so creepy to hear, but we're gonna do it. Okay,
Consider a typical computer operation, a program performing I/O. To start an I operation, the device driver loads the appropriate registers in the device controller. The device controller, in turn, examines the contents of these registers to determine what action to take. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver that it has finished its operation. The device driver then gives control to other parts of the operating system, possibly returning the data or a pointer to the data if the operation was a read. For other operations, the device driver returns status information such as write completed successfully or device busy. But how does the controller inform the device driver that it has finished its operation? This is accomplished via an interrupt. 1.2.1.1 overview. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. Interrupts are used for many other purposes as well, and are a key part of how operating systems and hardware interact. When the CPU is interrupted, it stops what it is doing and immediately transfers execution to exit location. The exit location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes the interrupted computation. A timeline of this operation is shown in Figure 1.3. To run the animation associated with this GUR, please click here. Interrupts.
Can I actually click it? Maybe this is online somewhere. Yes, the publisher's website has. Oh, okay. The actual. The author of the book. Okay, let's bring this up. So this is the author of the book, William Stallings. Okay, cool. 12-time award winner for the Texty. What's the Texty Awards? Textbooks excellent. I love that. I want to write a textbook one day. He wrote a lot of books. Damn. Crypto network security. So he just be sitting around writing books. Yeah, he just be writing textbooks. He's a writer. He knows his stuff. That's so dope. See, this to me is cool. I don't know what other people's definition of dopeness is, but to me, this is dopeness. And he's a teacher. Oh. This is his website. It's like resources for computer science and whatnot. Homework, technical writing. Dang, so he just been working. All sorts of stuff. This is a rabbit hole. Okay, I might have to come back and explore this later on, but I love stuff like this. And you can tell that he's been around for a while because he has just such a mountain of things. Okay, computersciencestudent.com. I like this. I like it. I want it. Okay, so this is the author. He's written all these textbooks. Where's he from? "17 titles and counting, revised editions, total of 40 books of various aspects on these subjects." Okay. See, I want to write a textbook myself. This is one of the top 5 most viewed LinkedIn profiles on LinkedIn for 2012. Okay. Dang. Yeah, I want to write a textbook too. My master's degree is in illustration, visual art, sequential storytelling, and entertainment design. I don't know though. I feel like it would take some audacity for me to write a textbook about that from the vantage point of me never worked in a production company. But I feel like I've been working in that field, but just not in that way. I've been taking a non-traditional path, especially with the AI stuff and how I do it with like engineering. But yeah, I want to write a textbook one day. I want to write several textbooks. I want to be very well published. That's like just a life goal for me. And I've created some books, but they were like done for an organization, and so they're never going to see the light of day. Okay, cool. So the one that I'm reading is Operating System Concepts. I don't even see it in here, in this list here. Anyways, the reason why I came here was to look at these animations. And they're supposed to be figure 1.3. Okay. Well, I went to the wait, who's the publisher of this? Oh. Maybe this is not the right book. Oh, you know what? Y'all, I think I might have been looking at the wrong thing. I think this is it. This is a book cover. Okay. Oops, my bad. I just promoted a whole nother person. Well, at least I discovered a cool person. I might have to come back and check him out. This is not the person, but apparently he is also in the same space. This is the book. These are the authors. Avi Silberschatz, Peter Bear. I like that name, Bear. That's nice. Galvin and Greg Gagne. And they have PowerPoint presentations for this. Ooh, I really don't want to go into this, but let me go ahead and open it up. I just want to see one. If it's worth it, then I might get some more of these later on. I really don't like downloading a bunch of stuff like this, though. I have PowerPoint on my computer. When did I get PowerPoint? Oh yeah, I used to subscribe to Microsoft, that's why. Okay, well hopefully it still works. Yeah, it'll let me look at it, I guess, but not edit. Okay. Well, this is nice to know that this exists. Yeah, this isn't what I'm looking for. I want the animations that it's referencing. Why don't y'all hear me? Okay. Well, that's fine. Let me not get too distracted by this, I guess. But I would love to see the animation. Maybe it's on YouTube. Okay, I'm just gonna check one time and then I'm done. Um, operating system interrupt. Let's watch this video together. This is probably good enough. Let's get that volume up there.
So, an interrupt is a signal sent to the device or the software of the operating system. It causes the operating system to temporarily stop what it's doing and service that interrupt using the interrupt handler. If required, less important functions are overridden or delayed. So let's take a look at some examples of interrupts.
Okay, he's speaking very slow.
First example could be a hardware error, such as a paper jam in a printer, a disk drive being ready to receive more data. Maybe the user has pressed Ctrl-Alt-Delete to interrupt the current process manually. Maybe a software error has occurred. Or maybe if you're using a smartphone, you're receiving a call on your device. Some interruptions require human intervention. For example, that paper jam can't fix itself. While other interruptions don't require any intervention at all by humans, they just go on in the background of the computer without us even knowing about them. So, why are interrupts important? Well, a computer can technically only run one program at a time. A processor simply can't process all the demands made on it by all the programs at once. So the ability for applications to interrupt each other gives the illusion of multitasking, a feeling that many programs are actually running at once. In reality, they are time-sharing, using scheduled interruptions.
Oh, okay.
Earlier on, we mentioned it's the job of the interrupt handler within the operating system to handle the interrupts. The interrupt handler will prioritize the interruptions and place them in a queue ready to be handled. If we look at the diagram, we can see how this happens. We have our current task, and then we receive an interrupt signal. It's now that the interrupt handler takes over and stops the task that you're doing and makes a note of the current status of that task, so it can be resumed later on. The interrupt is then serviced and taken a look at. If needs be, we can then carry on with the current task if it's of a higher priority, or the interruption may take precedence and be handled first.
Okay, that makes sense. Then the other question I had was for an IO device, can you explain the difference between the device controller and driver? Question mark. Ugh. Okay, so it says here Let's go ahead and get Speechify involved in this. Oh, I don't have it on here. Let me switch my browser. It's on the Chrome. Okay, where's my rain? My music. Okay.
Let me break down the differences between device controllers and device drivers and explain where each lies. Device controller. This is
Lives.
hardware, a physical electronic component. Lives on or with the device itself, like a chip on your hard drive or network card. Handles the actual electrical signals and low-level operations. Has its own simple processor and local buffer memory. Example, a hard drive controller manages the physical spinning of platters and movement of read-write heads. Device driver. This is software computer code. Lives in the operating system, usually part of the kernel. Translates OS commands into specific instructions the controller can understand. Handles error processing, buffering, and scheduling. Example, a hard drive driver knows how to convert save file into specific commands the drive controller understands. The relationship works like this. Copy application operating system device, driver device controller physical device. Think of it like this. If you're driving a car, the device controller is like the car's engine control unit, ECU. The device driver is like knowing how to operate that specific car, where the pedals are, how sensitive the steering is. You, the application, just say, go faster. The driver knows how to press the pedal, and the controller knows how to adjust the engine. Would you like me to elaborate on any part of this explanation?
No, I'm good, bro. Thanks. I'm good. Not passing that. Okay, so that's good. Let's continue.
Are an important part of a computer architecture. Each computer design has its own interrupt mechanism, but several functions are common. The interrupt must transfer control to the appropriate interrupt service routine.
Let me also turn the scroll back on as well. Enable scrolling. Yeah. Okay.
The straightforward method for managing this transfer would be to invoke a generic routine to examine the interrupt information. The routine, in turn, figure 1.3 interrupt timeline for a single program doing output, would call the interrupt specific handler. However, interrupts must be handled quickly, as they occur very frequently. A table of pointers to interrupt routines can be used instead to provide the necessary speed. The interrupt routine is called indirectly through the table, with no intermediate routine needed. Generally, the table of pointers is stored in low memory. These locations hold the addresses of the interrupt service routines for the various devices. This array, or interrupt vector, of addresses is then indexed by a unique number given with the interrupt request to provide the address of the interrupt service routine for the interrupting device. Operating systems as different as Windows and Unix dispatch interrupts in this manner. The interrupt architecture must also
Let's go
save
back.
the information of whatever was
Let's go
interrupted,
back.
so that it can restore this information. But would call the interrupt specific handler. However, interrupts must be handled quickly, as they occur very frequently. A table of pointers to interrupt routines can be used instead to provide the necessary speed. The interrupt routine is called indirectly through the table, with no intermediate routine needed. Generally, the table of pointers is stored in low memory. These locations hold the addresses of the interrupt service routines for the various devices. This array, or interrupt vector, of addresses is then indexed by a unique number given with the interrupt request to provide the address of the interrupt service routine for the interrupting device. Operating systems as different as Windows and Unix dispatch interrupts in this manner. The interrupt architecture must also save the state information of whatever was interrupted, so that it can restore this information after servicing the interrupt. If the interrupt routine needs to modify the processor state, for instance,
Okay, so the interrupt architecture must also save the state information of whatever was interrupted. Oh, wow! I didn't realize all that was happening. Wow. Okay.
by modifying register values, it must explicitly save the current state and then restore that state before returning. After the interrupt is serviced, the save return address is loaded into the program counter and the interrupted computation resumes as though the interrupt had
Resumes.
1.2.1.2
Okay.
implementation. The basic interrupt mechanism works as follows. The CPU hardware has a wire called the interrupt request line that the CPU senses after executing every instruction. When the CPU detects that a controller has asserted a signal on, the interrupt request line, it reads the interrupt number and jumps to the interrupt handler routine by using that interrupt number as an index into the interrupt vector. It then starts execution at the address associated with that index. The interrupt handler saves any state it will be changing during its operation, determines the cause of the interrupt, performs the necessary processing, performs a state restore, and executes a return from interrupt.
Wait, so this is making me think about like, I don't know if y'all are old enough or if the people watching this are old enough, but I don't know if y'all remember back during the Windows XP, Windows 98, Windows ME, Millennial Edition era. Sometimes if you were doing something, you would get like all of a sudden a blue screen, like your computer would just crash. I wonder if this has anything to do with that. Like you're running an application and it's whatever its interrupts or something is doing is causing an issue with the memory so that it cannot resume properly. I'm wondering if that is like a part of that, or if there's any relationship between that. Interesting, because there must be some type of bug that can happen with that.
Execution state prior to the interrupt. We say that the device controller raises an interrupt by asserting a signal on the interrupt request line. The CPU catches the interrupt and dispatches it to the interrupt handler, and the handler clears the interrupt by servicing the device. Figure 1.4 summarizes the interrupt-driven Y-O cycle. The basic
YO cycle. Okay, what's 1.4? Okay. So the CPU, the driver initiates IO. Okay. Okay, error generates interrupt signal. Okay. Okay. Okay, I see what's happening. So the CPU is like minding its business basically. And here she come and she is like, yo, I got something for you to do. And the CPU is like, oh, word? Okay, I got you. Let me go ahead and get that done. And then when it's done, it's like, okay, we good. And then the thing is like, yeah, we good. And then the CPU is like, okay, I'm gonna go mind my business again. I'm good too. Peace. That's basically what this is saying, okay, for y'all out there. Because you know I'm a translator. Okay, let's continue.
interrupt mechanism just described enables the CPU to respond to an asynchronous event, as when a device controller becomes ready for service.
Oh yeah. So working with like a device, an I/O device is an asynchronous thing. Anytime you have a separation of infrastructure, or even system, that is inherently asynchronous. Where are we at here? Okay.
However, we need more sophisticated interrupt handling features. 1. We need the
Handling.
ability to defer interrupt handling during critical processing. 2. We need an efficient way to dispatch to the proper interrupt handler for a device. 3. We need multi-level interrupts so that the operating system can distinguish between high and low priority interrupts and can respond with the appropriate degree of urgency. In modern computer hardware, these three features are provided by the CPU and the interrupt controller hardware. 1O controller. Device driver initiates VO. Most CPUs have two interrupt request lines. One is the non-maskable interrupt, which is reserved for events such as unrecoverable memory errors. The second interrupt line is maskable. It can be turned off by the CPU before the execution of critical instruction sequences that must not be interrupted. The maskable interrupt is used by device controllers to request service. Recall that the purpose of a vectored interrupt mechanism is to reduce the need for a single interrupt handler to search all possible sources of interrupts to determine which one needs service. In practice, however, computers have more devices than they have address elements in the interrupt vector. A common way to solve this problem is to use interrupt chaining, in which each element in the interrupt vector points to the head of a list of interrupt handlers. When an interrupt is raised, the handlers on the corresponding list are called one by one until one is found that can service the request. This structure is a compromise between the overhead of a huge interrupt table and the inefficiency of dispatching to a single interrupt handler. Figure 1.5 illustrates the design of the interrupt vector for Intel processors. The events from 0 to 31, which are non-maskable, are used to signal various error conditions. The events from 32 to 255, which are maskable, are used for purposes such as device-generated interrupts. The interrupt mechanism also implements a system of interrupt priority levels. These levels enable the CPU to defer the handling of low-priority inter. Vector number OT23, a 567891000.
Okay, it's trying to read something it shouldn't be reading. Okay, so let's just bring it back a little bit. I'm gonna take a break here in a second too. Recall the purpose of vector interrupt mechanism. So basically, the vector interrupt vector. Okay, an array of addresses with unique numbers. One second. I need eggnog. This is a lot to think about. I need eggnog. I need like the last few bites of an egg sandwich I made earlier today to calm my nerves. Okay. Explain what an interrupt vector is. I like to make sure that my responses are optimized for text to speech, or otherwise it'll try to read a table or some code or something weird.
The interrupt vector is a special table in your computer's memory that helps manage emergencies. Picture it like a phone book for your computer. When something urgent happens, like you pressing a key or new data arriving, that's called an interrupt. The computer needs to know who to call to handle this emergency. Each type of emergency has its own number, called a vector number. When an emergency happens, the computer looks up this number in its phone book, the interrupt vector table. This table tells the computer exactly where to find the instructions for handling that specific type of emergency. For example, if you press a key, that might be interrupt number 1. The computer looks up number 1 in its table and finds the address of the keyboard handler program. It then runs those instructions to process your key press. After handling the emergency, the computer goes back to what it was doing before. Think of it like this. If you have different emergencies at home, you might call different people. A plumber for water issues, an electrician for power problems. The interrupt vector is like having all these emergency contacts organized in one place, so you always know who to call. Would you like me to explain any part of this in more detail?
um, explain the interrupt request line. Oops, this is getting a little easier. And interrupt and yeah.
Let me explain both parts clearly for speech. First, the interrupt request line. Think of it as a doorbell wire that runs from devices to your computer's processor. When a device needs attention, it sends an electrical signal through this line. It's like different devices ringing the doorbell to say, hey, I need help. For example, when you press a key on your keyboard, it sends a signal through its interrupt request line. Now, the interrupt handler routine. This is a special program that runs when the doorbell rings. When a device signals an interrupt, the processor stops what it's doing and runs this handler program. The handler is like a trained specialist who knows exactly what to do for each type of interrupt. Here's how they work together. Your keyboard detects a key press. It sends a signal on its interrupt request line. The processor stops its current work. The processor saves what it was doing. The interrupt handler runs and processes the key press. After finishing, the processor goes back to its previous work. This is similar to how a doctor's office works. The interrupt request line is like pressing the call button, and the interrupt handler is like the nurse who comes to help when you press it. Would you like me to explain more about any part of this process?
Stop asking me if I want you to explain more, bro. I'll let you know exactly what I need. Okay. I want to see what it says. Got it. Yeah, you know that's right. You know that's right. I know you got it. Do you? Do you? Cause I do. I'm just checking. Okay, so let's continue.
Interrupts without masking all interrupts and makes it possible for a high priority interrupt to preempt the execution of a low priority interrupt. In summary, interrupts are used throughout modern operating systems to handle asynchronous events. Device controllers and hardware faults raise interrupts. To enable the most urgent work to be done first, modern computers use a system of interrupt priorities. Because interrupts are used so heavily for time-sensitive processing, efficient interrupt handling is required for good system performance.
Okay.
1.2.2 storage structure. The CPU can load instructions only from memory, so any programs must first be loaded into memory to run. General purpose computers run most of their programs from rewritable memory, called main memory, also called random access memory, or ROM. Main memory commonly is implemented in a semiconductor technology called D-dynamic random access memory. Computers use other forms of memory as well. For example, the first program to run on computer power on is a bootstrap program, which then loads the operating system. Since RAM is volatile, loses its content when power is turned off or otherwise lost, we cannot trust it to hold the bootstrap program. Instead, for this and some other purposes, the computer uses electrically erasable programmable read-only memory and other forms of firmware storage that is infrequently written to and is non-volatile. EEPROM.
Wait, let's go back.
Storage definitions and notation. The basic unit of computers. Computers use other forms of memory as well. For example, the first program to run on computer power on is a bootstrap program, which then loads the operating system. Since RAM is volatile, loses its content when power is turned off or otherwise lost, we cannot trust it to hold the bootstrap program. Instead, for this and some other purposes, the computer uses electrically erasable programmable read-only memory and other forms of firmware storage that is infrequently written to and is non-volatile. EEPROM. Storage definitions and notation. The basic unit of computer storage is the bit. A bit can contain one of two values, and one. All other storage in a computer is based on collections of bits. Given enough bits, it is amazing how many things a computer can represent. Numbers, letters, images, movies, sounds, documents, and programs, to name a few. A bile is 8 bits, and on most computers,
bile.
it's the smallest convenient chunk of storage. For example, most computers don't have an instruction to move a bit, but do have one to move a byte. A less common term is word, which is a given computer architecture's native unit of data. A word is made up of one or more bytes. For example, a computer that has 64-bit registers and 64-bit memory addressing typically has 64-bit words. A computer executes many operations in its native word size rather than a byte at a time. Computer storage, along with most computer throughput, is generally measured and manipulated in bytes and collections of bytes. A kilobyte, or KU, is 1,024 bytes. A megabile, or MI,
Megabile.
1,252
Megabile.
bytes.
Sounds like a band, a rock
Or
band.
DB is 1,024 bytes. A terabyte, or TB, is 1,024 bytes. And a petabyte, or IB, is 1,024
It is not reading any of this
bytes.
correctly.
Computer manufacturers
It's not getting the
often round up these
exponents.
numbers and say that a megabyte is 1 million bytes, and a gigabyte is 1 billion bytes. Networking measurements are an exception to this general rule. They are given in bits, can be changed, but cannot be changed frequently. In addition, it is low speed, and so it contains mostly static programs and data that aren't frequently used. For example, the iPhone uses EEPROM to store serial numbers and hardware, information about the device. All forms of memory provide an array of bytes. Each byte has its own address.
Okay, so there's a different type of memory EEPROM. I never heard of that before. Tell me about. Oh. Okay. So how? What am I trying to say here? If RAM works differently in terms of how memory is written, explain the difference. It's so weird getting to the C button because it's like my middle finger right down below. I'm used to kind of just using my. I really have like a hybrid. I don't do like true touch typing with the regular keyboard. I do like kind of a mix of that and like gamer keyboarding. Okay, let's go ahead and read this now.
RAM, random access memory, handles memory writing very differently from EEPROM. Here's how. RAM writing is much simpler and faster. It works by directly changing the state of transistors and capacitors. When you write to RAM, it's like flipping electrical switches. The process is almost instant and can happen billions of times per second. The key differences in writing are: RAM can write to any location instantly. All memory locations in RAM can be written at the same time. No erase cycle is needed before writing. Writing doesn't wear out RAM cells like it does with EEPROM. EEPROM writing is more complex. First needs to erase the existing data. Can only write byte by byte. takes much longer, milliseconds instead of nanoseconds, has a limited number of write cycles. It's like comparing a whiteboard to a scratch-off lottery ticket. RAM is like the whiteboard you can instantly erase and write anywhere. EEPROM is like the lottery ticket. You need to carefully scratch off the old content before writing new information, and you can only do this so many times before damaging the surface. In RAM, changing transistor states means switching them between two voltage levels, either charged usually around 5 volts or uncharged 0 volts. Each bit of data is stored using a combination of transistors and a tiny capacitor. When the transistor is switched on, it lets electrical charge flow into the capacitor. When it's switched off, the capacitor discharges. This creates our binary states. Capacitor charged high voltage equal to 1. Capacitor discharged low voltage equal to 0. It's like a tiny bucket capacitor with a tap transistor. Opening the tap, turning transistor on, lets water electrical charge fill the bucket. Closing the tap, turning transistor off, keeps the water in. But these RAM capacitors are very leaky buckets. They lose their charge quickly. That's why RAM needs constant power to refresh these charges and keep the data intact. This is totally different from EEPROM, which traps electrons in a special layer of the chip to store data permanently, even without power.
Okay, so RAM needs to be okay.
Yes, RAM absolutely needs constant power to maintain its state. This is because of how those capacitors work. Think of each RAM cell as a tiny bucket that keeps leaking. The electrical charge stored in the capacitors naturally drains away very quickly, in just a few milliseconds. To prevent data loss, RAM constantly needs to check the charge level in each cell, recharge cells that are supposed to be storing a 1. This checking and recharging happens thousands of times per second. This is called memory refresh. Without power to keep this refresh cycle going, all the capacitors discharge and the data is lost. This is why when your computer loses power suddenly, anything stored in RAM disappears. This is the big difference between RAM and storage devices like EEPROM or hard drives. They use methods that physically trap electrons or create magnetic patterns that stay stable without power, while RAM's storage method needs constant electrical maintenance to keep the data intact.
How long does RAM maintain residual state after losing power? Can this be forensically inspected? That's an interesting question because it raises a security issue for me, I guess. Like, if RAM is volatile, then the loss of power indicates that it's going to lose that memory. But if it doesn't lose all of it, maybe what like is it possible for a capacitor to just still maintain voltage for an unexpected amount of time that is like long enough for it to be I guess for it to be recovered possibly, or I don't know. Let's see what it says.
RAM data doesn't instantly vanish when power is cut. This is called ROM remnants. The data can persist for seconds to minutes, especially in cold temperatures. When RAM chips get colder, the electrical charge leaks away more slowly. This creates a potential security issue. If someone quickly reboots a computer and boots to a different operating system, or uses liquid nitrogen to cool the RAM chips, they might be able to read sensitive data that was in memory. This is why secure systems often overwrite RAM before shutdown, require a waiting period between reboots, have physical security to prevent cold boot attacks. Cold boot attacks work like this: freeze RAM chips to extend data lifetime, quickly transfer them to another system, dump the memory contents for analysis, find encryption keys, passwords, or other sensitive data. Modern RAM tends to lose data faster than older RAM, and some computers now clear RAM on power loss. But the risk hasn't completely gone away, which is why high security systems need special memory handling procedures.
Okay, so that's crazy. I don't know why my thoughts went to like, did they do this at Diddy's house? You know what? Let's not even go there. I don't want to be mean. But that was the first thing I thought, because like whenever somebody gets in trouble with like the FBI or people go to investigate, that's the first thing people try to do is like erase what's on the computers. So this was like, is that what they had did when they went to his place? I wonder. Or the other guy. I don't want to say names, but yeah. So when they go and like raid a house, do they take liquid nitrogen with them to do this? I'm so curious. So when I don't know how to say this, when an enforcement agency does a raid, do they do this sort of technique? How long can RAM memory be preserved this way? Can use cold boot attacks during raids for digital evidence collection. Here's how they typically handle it. If they find a running computer, they might use wow. 5 to 10 minutes. This is so fascinating.
Live memory capture is done through specialized hardware and software tools while the computer is still running. Main methods include hardware methods, PCI cards that plug into the target system, FireWire devices that exploit DMA direct memory access, Thunderbolt or USB devices with special capture capabilities, software methods, memory imaging tools like FTK Imager or Memorize, forensic operating systems like SAN SIFT, custom kernel modules or drivers, Windows crash dump tools. The process typically goes: connect capture device or run capture software, create a bit-by-bit copy of RAM contents, calculate hashes to verify the copy's integrity, store the memory dump for analysis. This captures everything in active memory, running processes, network connections, decrypted data, system passwords, browser data, command history. The challenge is capturing memory without altering it, since the capture process itself uses some RAM. That's why hardware methods are often preferred for critical forensics.
Okay, next question is there, okay, wait, let's go back. If my computer lost power all of a sudden, is there a way I could restore or could dump or could access the RAM if I restarted really quickly? Oh. Mm. Oh, it thinks I'm trying. It says I could. I don't want unauthorized access. I'm just asking. Calm down. See a hit dog holler. You must be. You must be trying to be up to something. I'm not up to nothing. I just want to know. These techniques are restricted to legitimate law enforcement, security professionals conducting authorized investigations. If you've lost data due to power outage, okay. This is in regards to my own computer. I'm learning. That's why. What did I do? Okay, it was freezing up. I must have gotten to my other mode. That's why I asked. Stop tripping. Oh, no, 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 no. I don't want to do them. Okay, I feel like I'm digging myself into a hole here. You know, one thing I've also realized too is like there are a lot of things that like are not illegal with computers, but they are definitely obscure to find information about, and it gets tricky because it's like I feel like you should be able to learn anything you want. I feel like that's what freedom of information means, but the thing that should be policed is what you do with that information. But sometimes these AI bots are way too. I understand why, because you don't really know what people are up to these days. But at the same time, I don't need an AI bot that is, basically saying it's offering me access information, basically gatekeeping things. Yeah, it thinks I'm asking about. Yeah, my own work. Don't get it twisted. Don't get it twisted, baby. Okay. RAM contents are gone. There's no commercial software that can bring it back. This is different from hard drive recovery. So there's no commercial software, but there is software for. Let me see. Let me look this up. Like if I was a law enforcement. Recovery training. See, if I was a law enforcement recovery specialist, I could go to here. Okay, so there's actually a role for this. That sounds so fun. Sometimes I think about applying for like the FBI or something. I definitely see advertisements for it, but I don't know. I smoke weed. I would quit, I guess, but I'm not really. Yeah. Um, that would be such an interesting job, though. Just the technology involved. Oh, Windows. Never mind. Never mind. I don't want to do that with no Windows computer. Maybe Linux. I guess I wonder if like most cyber crimes are done on Windows computers. That would be wait. Most common operating system for cyber Windows is the most popular. Oh, it's the most popular target. Um, okay, I wouldn't be surprised if it's the one that's the most commonly used for cyber crimes and whatnot as well. Um, digital forensics. That would be maybe that's what I need to go into. Digital forensics. You have to be a law enforcement officer, agent, direct law enforcement support personnel, or employee of a state, federal, local, tribal, international institution performs functions directly related to a law enforcement department of Homeland Security mission. Okay. Okay. I should just call and be like, hey, I don't satisfy any of these requirements. Can I do it? Can I just show up? What do their careers look like? This is a bit of a tangent. I'm gonna take a break here in a second anyway, so it doesn't really matter. DHS. Huh. Let me just have a little peek. Let me just have a little sneaky peek. Let's just look strictly by pay. I want only jobs that will pay 400,000. No, I'm just kidding. Let's see if we can find IT. Any type of IT. Nope. Oh, y'all don't pay. I see. Okay, that's not a lot. Not for a security clearance job. Okay, well, and y'all gonna definitely work somebody to the bone for this job too. I bet. Yeah, y'all gonna do all this right here. Must be able to obtain and maintain security clearance. I could definitely do that part. Okay, well, back to what I was doing. I was just curious about that. Okay, so you have to be somebody of a special credential to do it. Why is there no commercial products for this for personal use? Is there... Oh wait, that's not my full question. I didn't mean to press enter. Let's finish this. Is there a legal case that cause a law to be made? There's no specific law preventing Issues more technical and practical. Modern computers are designed to clear RAM quickly for security reasons. Built-in memory wiping or shutdown. Okay, I understand. Utilities, very low system access. This was poses security risks. Operating systems block this kind of access. Okay. Oh, I get it. So basically, it's not like illegal, but I guess it would be a huge risk for somebody to actually make this as a commercial product because of how it could be used. I get it. And nobody probably wants to put themselves in that situation. But I bet you probably have like companies that probably, maybe companies develop their own solutions when needed for this type of thing. Maybe like for their own systems, or maybe they can just buy. Well, okay, if you're like if you work for like a data center, and a data center has some extremely sensitive information that could potentially need to be saved in an extremely critical circumstance. Like for example, let's say you work for AWS GovCloud. You would think that they have a little bit of nitrogen on hand to dip a memory chip into every once in a while. You would think that they would have that as like their emergency kit, but I don't know. Okay, so if I did IT at a data that I just had a flashback to something. 1 second. That had okay. So, because I'm thinking like, okay, let's say I work for like Google, and Google's like, okay, we got to store the password for Google, like the master thing that every the center of the heart of Google. That's going to be somewhere stored in data somewhere, or like super secret private stuff. And you got to think like most data is protected because it is syndicated across a network of data centers that are basically, you know, creating redundancy. But I can imagine that there might be some data that you don't want to be redundant because the security risk of that data potentially being exposed in any one of those data centers is so high, and the data is so sensitive that it might be more secure to just keep that data in one place. But I guess in that situation, you would not be using RAM. But let's say that there's this data, but then there's like the process that data actually causes to run. And that process itself needs to be, like what happens if something happens during that process where some data has not been written or something. I'm trying to think of like an example in which this might be like a necessary part, but maybe I'm overthinking this. Can you reference the pertinent laws referring to? Also, am I allowed to ask, or no, will I get in trouble for asking? That's what I want to know. Because I'm not going to ask for me in trouble. Y'all watching, y'all see this. Okay, no, you won't get in trouble for asking questions. That's what I thought. That's what I thought. Okay. Curiosity, this is completely normal. I apologize for sounding overly cautious. There's actually is a specific law that here. Okay, the main laws that come into play are about how technique is used, not technique itself. Redefined abuse makes unauthorized access to computer systems legal. Yeah, of course. Data protection laws like GDPR and CCPA control how personal data can be handled. Okay. Asking questions about how computer memory work is perfectly legal. It's only the actual unauthorized access of systems or data that becomes a legal issue. Um, what are the legal limits for what a and also too never mind. It was like I know it's AI, but it's like responding like, "Oh, I'm sorry, I misunderstood what you thought, what you would say. I thought you meant this. You're a computer. You didn't think nothing." But whatever. Um, okay, so what are the legal limits for what a person can do with their own system in this regard? I think this is a good question as well, too. A good line of questions because I used to work in computer maintenance. I was an easy tech at Staples, and that's not like a super techie job or anything. But one of the parts of that job was that a lot of times people would come in because their computer had crashed, died, or frequently dies. Maybe their computer is has a disposition to turn off all of a sudden, like when it gets really hot. And sometimes it has turned off or will turn off when they're doing really critical things. Now, this is well beyond this, but I just know that sudden loss of state is like a big issue, especially for older systems that need to be replaced, honestly. So it almost makes me think like, well, why don't we design RAM in a way that allows for this type of forensic thing to be used responsibly for commercial usage? Because people, people sometimes don't save things that they're currently working on, you know? And it would be so nice if you just knew, like, okay, if I can do X, Y, and Z within a certain amount of time, then I think I can get my stuff back. Why does this say error? Oh, okay. Okay. Experiment with your system's memory. Okay. What's DRM? Digital rights management. Breaking your own encryption is legal. Okay. Okay. That's interesting. Okay, I'm gonna take a break here. I've been streaming for a little bit under 3 hours, so it is well deserved. We're gonna get back on track, and what's this, page 12? Where are we at? I'm gonna come back and try to finish a couple more sections of this. We could try to get to 1.4. Yeah, we'll try to get to 1.4. Maybe like another 10 pages. I'm gonna try to speed this up too. It took me a little bit to get set up, but now I think we're good. Okay, don't go too far, but if you go anywhere, just know you can always come on back to the Wolfpack. I'll be right here where you left me. Oh! Y'all, I'm back, but as you can hear in the background, I have an angry puppy. Let me change my audio source here because he gonna bark for a little bit. I took him out to go potty, which is what I normally do when I take a break. Normally, I take him out to potty, let him run around just for a little bit, especially this time of night because that's his last chance to go out before tomorrow morning. So, by this time of night, he doesn't know whether he's tired or whether he wants to play. So basically, when I take him outside, I'm just like, bro, this is not playtime. He wanted to run around, so I let him. Well, a little bit nothing I could do about it because I didn't take him with his leash, so he was just out in the back, fenced in area, just running around. I was just trying to let him come back in. So, anyways, he's displeased with me. He's upset at his whole life. He's being emo. He's a preteen, I guess. Now he's at the 5.5 month or so mark. So. Actually, he does crate pretty well. Let me just say that. Let me give him some credit. He crates really well. I hardly have any problem with him crating. He doesn't do excessive barking or anything, so I won't even make it seem like that's a problem because it really isn't. He takes to it very well. So I think just the past couple of days have been really hard for him because he has a cold basically. First of all, well, let me just say this. I did not know that a dog could get a cold. Like, it makes perfect sense. Like, I feel silly for not thinking about that or realizing that. I didn't know dogs got colds like that. I also did not know that dogs could cough, like congestion and everything like that. My dog was verklempt. You know what I'm saying? He was just like, so anyways, I think he must have caught something from he goes to this doggy, what's it called? Life Skills 101 class. And everybody there is vaccinated, so I'm not too worried about that part. But just like any other place with children running around, which is basically what they are. They're basically little baby infant puppies. And they're all gross basically. So yeah, he got some from that. But yeah, he's getting better. He wasn't like deathly sick, but it was just like the first time I ever seen him like sick. So yeah, I haven't been letting him run around as much just because I don't want that's like one of the advices that I got was it's like if your dog is like sick, don't let him run around too much. It'd be too wild or whatever. Just hydration, food, sleep, that kind of thing. Okay, but if he's like still like coughing and stuff by like let's say like Monday, then I'm probably gonna take him in just to get looked at just to make sure it's not something else. I read 5 to 7 days, as long as you don't see any like other disturbing things. So I'm just gonna go with that. Okay. So where were we? Okay. Let's continue. So I'm gonna try to read like maybe one or two more sections, but I really need to speed this up because I'm going very slow and I'm getting caught in a lot of like rabbit holes. And I want to actually finish this
Interaction is
book
achieved through a sequence of load
or
or
get really
store
far into it.
instructions to specific memory addresses. The load instruction moves a byte or
Well,
word from main memory to an. All forms of memory provide an array of bytes. Each byte has its own address. Interaction is achieved through a sequence of load or store instructions to specific memory addresses. The load instruction moves a byte or word from main memory to an internal register within the CPU, whereas the store instruction moves the content of a register to main memory. Aside from explicit loads and stores, the CPU automatically loads instructions from main memory for execution from the location stored in the program counter. A typical instruction execution cycle, as executed on a system with a von Neumann architecture, first fetches an instruction from memory and stores. That
you
instruction.
can't use words like that and me not look it up. A von Neumann architecture. What the flip is that? That was not spelled right, but whatever. Close enough. Programs and data share the same memory space. Uh, one thing I do not like is when somebody discovers something and they name it after themselves. I don't know why. I just don't like that. It feels very cringy to me. Okay, connection online. It feels very cringy to me because one, usually a lot of things that we think were discovered by one person were oftentimes simultaneously discovered by multiple people who may not even know each other or know of each other's work. But typically, we will pick and choose who gets to get like the acclaim, and usually it's in a racial way, but also it usually is very sexist as well and all the other stuff. So I don't like when people have things named after them. That just doesn't sit well with me in general. I feel like they should just call things what they are instead of naming them after people. Okay, so it's okay. So is there another type of architecture aside from this one? Like a competing architecture? Oh, I'm on my layer. Um, is there another architecture on the side? Well, I really don't want to spell von Neumann, but I'm going to do it. I missed my question mark again. Excuse me. I think I've been pressing like Z instead of Control or Shift. I mean, okay, Harvard architecture. Make a table to pair and include pros and cons. Von Neumann. Von Neumann architecture. I'm gonna use that word in a sentence this next week just because I can. Okay, we gotta copy this into Markdown. Um, Command space because it doesn't like to render tables and stuff very well in here. So we're gonna do it over here like this, and like there. Actually, we can just reuse this other one. Command A and Command B. Separate cache, but shared main memory. So there can be parallel access. It's more secure. Why is the Harvard architecture not used in commercial computers? Yeah, there you go. Nah, no. Oh, I'm pushing Z, that's why. There we go. Higher power consumption. Fix my green screen. There we go. Can't mess up the illusion. Okay, so it's a higher cost, more power, more expensive. Saw software becomes complex. Yeah, I bet. Oh, interesting. Um, any. Oh, microcontrollers. Okay, that makes sense. That makes sense now. Embedded systems. Okay, my dog has stopped his whining. He is now chillaxed, apparently, so I can go back to my Logitech audio here. Hey, can you type? Okay. Um, Microcontrollers. Okay. Oh, gaming controllers. Um, okay. That's probably a dumb question. Okay, used for single purpose devices, systems that one run. Okay. When I type with this split keyboard, I'm noticing a lot more the lack of sensitivity and dexterity in my right pinky, which I had never noticed because when I started paying attention to how I type, I realized that when I type, I actually do not type with full 10 finger touch typing. I actually do all five of these fingers, but then with with this hand, I more or less kind of peck. So I'm like typing really like this. But now I'm trying to change that for ergonomic reasons, and it's very strange. It's very strange. It's a weird feeling. Um, AVR operating systems, free RTOS. What's that? It's an operating system for microcontrollers and small. Okay. Hmm. What is this? Please tell me this is a real thing someone's making and not just an AI picture because it looks super cool. Okay, so that's that one. What's the other one? Nut X. That's a weird name. I tell you what. Oh, I spelled that totally wrong. Hope I don't get something X rated. Uh, Apache Software Foundation. Apache. Okay. So is it mature? Yeah, show is mature. Real time embedded operating system. Okay, real time operating. Okay, cool, cool. I wonder how Native Americans feel about the Apache Foundation's name. I mean, that's neither here nor there, but I've always been curious about that. Okay, so pick operation systems, DSP operating systems. They're called real-time operating systems, and they minimal user interface, run specific tasks only, handle time and critical operations, manage hardware resources, don't support program installation. No major attempts have been made for a general purpose operating system because hardware limitations make it impractical. No demand for such systems. We need special software ecosystem. Can't run standard applications. Development would be very expensive. Um, so when I write software for an embedded device, is it how is it that the software can run a microcontroller? Okay, so I guess another question for me is or does a difference in system architecture mean a difference in hardware? Okay. This is one of those things where I'm like, where would I be able to learn specifically about this? Maybe if it's not in this book, I would have to talk to somebody who really knows themselves, because I just feel like there's like this like level of like computer science stuff where you're just not going to find it in a commercial book like this. But anyways, that's fascinating, interesting. Thank you. Let's
Instruction register.
keep pushing.
The instruction is then decoded and may cause operands to be fetched from memory and stored in some internal register. After the instruction on the operands has been executed, the result may be stored back in memory. Notice that the memory unit sees only a stream of memory addresses. It does not know how they are generated by the instruction counter, indexing, indirection, literal addresses, or some other means, or what they are for. Accordingly, we can ignore how a memory address is generated by a program. We are interested only in the sequence of memory addresses generated by the running program. Ideally, we want the programs and data to reside in main memory permanently. This arrangement usually is not possible on most systems for two. 1. Main memory is usually too small to store all needed programs and data permanently. 2. Main memory, as mentioned, is volatile. It loses its contents when power is turned off or otherwise lost. Thus, most computer systems provide secondary storage as an extension of main memory. The main requirement for secondary storage is that it be able to hold large quantities of data permanently. The most common secondary storage devices are hard disk drives and non-volatile memory devices, which provide storage for both programs and data. Most programs are stored in secondary storage until they are loaded into memory. Many programs then use secondary storage as both the source and the destination of their processing. Secondary storage is also much slower than main memory. Hence, the proper management of secondary storage is of central importance to a computer system, as we discuss in Chapter 11. In a larger sense, however, the storage structure that we have described, consisting of registers, main memory, and secondary storage, is only one of many possible storage system designs. Most programs are stored in secondary storage until they are loaded into memory. Many programs then use secondary storage as both the source and the destination of their processing. Secondary storage is also much slower than main memory. Hence, the proper management of secondary storage is of central importance to a computer system, as we discuss in Chapter 11. In a larger sense, however, the storage structure that we have described, consisting of registers, main memory, and secondary storage, is only one of many possible storage system designs. Other possible components include cache memory, CD-ROM or Blu-ray, magnetic tapes, and so on. Those that are slow enough and large enough, they are used only for special purposes. To store backup copies of material stored on other devices, for example, are called tertiary storage. Each storage system provides the basic functions of storing a datum and holding that datum until it is retrieved at a later time.
I like that word,
The main
datum.
differences among the various storage systems lie in speed, size, and volatility. The wide variety of storage systems can be organized in a hierarchy according to storage capacity and access time. As a general rule,
I like this graphic. I should get this tattooed on me somewhere. Let's make a dope tattoo. So, storage device hierarchy. Why have I never seen anything like this before? I wonder what it would look like if we just started adding like database, cloud infrastructure. I mean, all that stuff kind of like ends up being in the realm of this hard disk. It's technically what it is. Okay. So provides basic functions of storing data and holding data until it is retrieved at a later time. The main difference among the various storages systems lie in speed, size, and volatility.
there is a storage capacity.
Auto scroll, where you at? Auto scroll is not scrolling. What is this? Process documents. He Um, I wonder what this does. I mean, it doesn't really say. We could try it. Um, okay, yeah, so let's do dark mode too.
Figure
Ugh.
1.6, Storage Device Hierarchy. Trade-off between
Wait,
size and
this is
speed,
too
the smaller
small.
and faster memory closer to the CPU. As shown in the figure, in addition to differing in speed and capacity, the various storage systems are either volatile.
Why is this way thinner? I can't read this. This is too. Mm. Oh, that's why. Yeah, stop playing with me. My eyes are not that good. These glasses do not work that well. Okay. Okay.
Memory closer to the CPU. As shown in the figure, in addition to differing in speed and capacity, the various storage systems are either volatile or non-volatile. Volatile storage, as mentioned earlier, loses its contents when the power to the device is removed, so data must be written to non-volatile storage for safekeeping. The top 4 levels of memory in the figure are constructed using semiconductor memory, which consists of semiconductor-based electronic circuits. NVM devices at the 4th level have several variants, but in general are faster than hard disks. The most common form of
Lost my
NVM
earbud.
device is flash memory.
Where are we? Okay, so the top 4 levels are semiconductor. An NVM devices at the 4th level. Non-volatile memory devices at the 4th level have several variants, but in general are faster than hard disk. Yeah, I remember when flash memory became like more popularized for long-term storage.
Which is popular in mobile devices such as smartphones and tablets. Increasingly, flash memory is being used for long-term storage on laptops, desktops, and servers. Since storage plays an important role in operating system structure, we will refer to it frequently in the text. In general, we will use the following terminology. Volatile storage will be referred to simply as memory. If we need to emphasize a particular type of storage device, we will do so. Non-volatile storage retains its contents when power is lost. It will be referred to as NVS. The vast majority of the time we spend on NVS will be on secondary storage. This type of storage can be classified into 2 distinct types. Mechanical. A few examples of such storage systems are HDDs, optical disks, holographic storage, and magnetic tape. If we need to emphasize a particular type of mechanical storage device tape, we will do so explicitly. Electrical. A few examples of such storage systems are flash memory, FRAM, and RAM in SSD. Electrical storage will be referred to as NVM. If we need to emphasize a particular type of electrical storage device, we will do so explicitly. Mechanical storage is generally larger and less expensive per byte than electrical storage. Conversely, electrical storage is typically costly, smaller, and faster than mechanical storage.
It's funny how life works
The
out like that.
design of a complete storage system must balance all the factors just discussed. It must use only as much expensive memory as necessary, while providing as much inexpensive, non-volatile storage as possible. Caches can be installed to improve performance, where a large disparity in access time or transfer rate exists between 2 components. 1.2.3i.
Wait,
Host
let's
structure.
unpack
A
that.
large portion of
That's like
operating system
the general definition of what cache is trying to achieve in any context. Can you define the general concept of cache? Yeah, I feel like I hear the word cache being used in a lot of different contexts. Okay. Uh, okay.
Code is dedicated to managing one zeroth, both because of its importance to the reliability and performance of a system and because of the varying nature of the devices. Recall from the beginning of this section that a general-purpose computer system consists of multiple devices, all of which exchange data via a common, figure 1.7. How a modern computer system
Okay.
bus, the form of interrupt-driven I/O, described in section 1.2.1 is NED for moving small amounts of data, but can produce high overhead when used for bulk data movement such as NVS I/O. To solve this problem, direct memory access is used. After setting up buffers, pointers, and counters for the I/O device, the device controller transfers an entire block of data directly to or from the device and main memory, with no intervention by the CPU. Only one interrupt is generated per block, to tell the device driver that the operation has completed, rather than the one interrupt per byte generated for low-speed devices. While the device controller is performing these operations, the CPU is available to accomplish other work. Some high-end systems use switch rather than bus architecture. On these systems, multiple components can talk to other components concurrently, rather than competing for cycles on a shared bus. In this case, DMA is even more effective. Figure 1.7 shows
Non-volatile storage I/O. That's the non-volatile storage, volatile storage. I need to have this part explained a little bit. Why doesn't it format this well? I don't like that. Um, let's use ChatGPT. Hmm. Well, that sounds like a risky thing to do.
You're right to think that there can be potential security concerns with Direct Memory Access DMA, primarily because it allows certain devices to access main memory directly, bypassing the CPU. Here are some key security considerations for DMA. Unauthorized memory access, because DMA allows devices to write directly to memory. A malicious or compromised device could potentially access or alter sensitive areas of memory without the CPU's oversight. This could lead to data corruption or leaks if a device writes data to unauthorized sections of memory. DMA attacks, known as DMA attacks. These occur when an attacker connects a malicious device, e.g. via Thunderbolt, FireWire, or PCIe, to a system. Since these high-speed interfaces often support DMA, a rogue device could access sensitive data in memory without authorization, making it a security risk for computers, especially if they lack protection mechanisms. Lack of CPU intervention. Since the CPU isn't directly involved in each byte or operation, it can't verify or manage every action performed by the device controller. This hands-off approach means there's less oversight, which can be a security concern if unauthorized data transfers are taking place. Vulnerable hardware interfaces. Certain high-speed I/O ports like Thunderbolt or PCIe may be more susceptible to DMA-related vulnerabilities. Many modern systems mitigate these risks by implementing IOMU Input-Output Memory Management Unit, which restricts device memory access and can prevent unauthorized access by mapping only approved memory regions for each device. Inadequate access controls. Without strict access controls, DMA-capable devices may inadvertently or maliciously access memory areas containing sensitive data, such as cryptographic keys or kernel data. Proper configuration and secure firmware can help enforce restrictions on what data DMA devices can access. How security is typically addressed. Modern systems use mechanisms like IOMU to limit which areas of memory a device can access, effectively reducing the risk of unauthorized memory access. Some systems also require explicit user permissions for certain devices to initiate DMA operations, adding an additional layer of control. Summary. While DMA can be highly efficient for performance, it does introduce potential security risks, particularly if safeguards like IOMU aren't in place. Implementing such protections is essential to secure systems that rely on DMA, especially in environments with high security requirements or multiple, potentially untrusted devices. You're right to think that there can be potential security concerns with direct memory access. DMA, direct memory access between applications on the same system, isn't a direct feature of most operating systems because DMA primarily facilitates data transfer between hardware devices and main memory, bypassing the CPU. However, there are cases where applications may interact with shared memory or hardware that supports DMA, which can introduce similar security concerns if not carefully managed. Here's how it applies. 1. Shared memory and DMA risks. When two applications share a memory region for inter-process communication (IPC), hardware with DMA capabilities, like GPUs or NICs, may be used to transfer data efficiently. If one application is compromised, it might attempt to use DMA to access or modify memory belonging to another application, leading to potential data leaks or corruption. 2. Security concerns for intra-system DMA. Lack of isolation. If DMA-capable devices can access a shared memory region used by multiple applications, there's a risk of one application inadvertently or maliciously accessing another's memory. Privilege escalation. Malicious applications could exploit poorly configured DMA access to perform unauthorized memory reads or writes, potentially gaining access to sensitive system resources or data. Memory corruption. If two applications write to the same memory location through DMA without proper synchronization, data corruption can occur. 3. Operating system protections. Modern operating systems mitigate these risks with several mechanisms. Memory isolation, virtual memory. Each application typically operates within its own memory space, and DMA operations are controlled by the kernel. The OS ensures that DMA cannot bypass these boundaries unless explicitly permitted. Input-Output Memory Management Unit, IMU, ensures that DMA devices only access memory regions explicitly assigned to them. Applications communicating with a shared DMA buffer are restricted to predefined memory ranges, limiting unauthorized access. Device drivers mediate DMA operations, ensuring only authorized applications can request DMA transfers. Drivers enforce permissions and often provide APIs for secure memory sharing. Kernel mediation. DMA interactions are generally orchestrated by the OS kernel. Applications request DMA transfers through system calls, which the kernel validates before execution. 4. Examples of secure DMA use cases and applications. GPUs and shared buffers. In graphics-intensive applications, multiple processes might share a GPU. The GPU's driver and IOMU restrict access to ensure one application cannot interfere with another's memory.
Okay, that's enough for me. Sometimes when learning about something that's like outside of my current realm of understanding, I get a little suspicious because I feel like it could tell me anything and I probably would believe it. So we're just going to continue with the book. Okay. Let's see how long this next section is. This will definitely be the last if I do this. It starts on page 15. Okay, I'm not going to make it through all this. I'm tired. I'm tired as heck. This has been a 4-hour stream anyway, so it's probably a good time for me to go ahead and get off of here. Let's go ahead and save this. And we did a good amount of typing. We got some studying done. Got a decent amount of reading done. So, okay. Well, I don't know what to say. I guess I'll catch you later. Thanks for coming by. And don't go too far. But if you do, you're always welcome to come back. Not just welcome, but encouraged to come back to the Wolf Pack. And I'll be right over here. Ah! Okay, I'll see you later. Bye. If you're still here, I want to invite you to do just one small little favor for me. Go down to the description below. There's a link to my survey, and I use this survey to help improve my channel. Right now, I'm actually doing some research to just better understand my audience and hopefully kind of pinpoint exactly what kind of stuff I should make in this next era. So if you fill out that little form for me, it only takes about 15 seconds to do. You'll be doing me a huge favor, which I'm super grateful for, but also you'll be helping out so many people because I'm going to make great content for them as well. And plus, on top of all of that, it's free, because it's YouTube. So, anyways, the best is yet to come. Support a brother out. Go ahead and like, comment, follow, subscribe, and do that survey. And I will catch you on the flip side. Adios.